We're now going to look at what is essentially the cornerstone of natural selection, adaptation. I want to begin by pointing out that the word is used in different ways, but they're both related to one another. There is the process definition of adaptation, the process by which organisms respond to changing environments by evolving a form or function that's better suited to new circumstances. So that is actually the process of adapting, another form of the word adaptation. But then there's the actual phenotypic definition, which refers to a specific trait that optimizes survival. In other words, you talk about a specific adaptation. In other words, some trait of the animal that enables it to compete successfully and therefore, hopefully, survive. Now, one thing that's important to understand about adaptation, does it imply evolutionary progress? Is being adaptive necessarily being better? Is it indicative of an improvement or not?
Evolution is not about progress in Darwin's sense. In Darwin's sense, under the theory of natural selection, evolution is adaptation to changing local circumstances. That's all it is, and that doesn't include a principle of progress. For example, suppose there's a herd of elephants in Russia and it's getting cold because there's going to be an ice age. Then there's natural variation among those elephants and how much hair they have. The ones that are hairier on average, not every single time, leave more offspring because they do better as the cold advances. And 100 generations down the line, you get woolly mammoths because the amount of hair accumulates. Now, suppose that happens. The woolly mammoth isn't the cosmically better elephant. It's just an elephant better adapted to the local circumstances of cold in Russia.
So no, adaptation does not imply progress. It implies exactly what it is, and that is somehow making adjustments that better enable you to survive in the light of changing environmental circumstances. Okay, one of the best examples, maybe the best example, I don't know, of adaptation, natural selection, speciation, this kind of wraps up so much about what I've been talking about in this section, and even some of the earlier sections, I think, is what occurred at the Galapagos Islands in the course of evolutionary history. Darwin visited the Galapagos Islands. He was the naturalist on board the HMS Beagle, and it went around South America and then ultimately ended up at the Galapagos, where he spent a fair amount of time collecting samples and noticing some really miraculous things that current researchers have been able to sort out even better. There's a group of birds on these islands, and they've been sort of named after him. In terms of the group, at least, they're called Darwin's finches, even though each one has a separate name. I'm going to show you a video, and I'll just let you know right now, it's a little bit over 12 minutes long, but it explains so much about what I've been talking about that it's really worth watching in its entirety.
13 species of finches, found in various combinations on the different islands. The birds live in diverse habitats.
The islands are very different from each other. They differ in size, they differ in topography, and in height.
Larger trees grow at higher elevations, while low islands have mostly cactus, grasses, and shrubs. In these diverse habitats, the finches have evolved many ways to survive. So, Rosemary, what's the important difference between these birds?
This little warbler finch with its very fine needle-like beak is perfect for picking off insects. This one is the woodpecker finch with a rather more robust beak. It concentrates on beetle larvae and termite larvae. Then we have the cactus finch with a much longer, sharp-pointed beak, which probes into cactus flowers. And then these three species are the large, medium, and small ground finches. So, Sean, the basic idea is the beaks are tools, and you need the right tool for the right job.
The finches look so different that Darwin first mistook them for entirely unrelated kinds of birds. How did the Galapagos end up with so many species of finches?
In terms of the actual history of the finches of the Galapagos, there were many different possibilities. Different kinds of finches could have all come from the mainland separately, or the finches could have all evolved out there on the islands. And what do we know about that?
Well, now we know from DNA evidence that all of the finches are more related to each other than any one is to a species on the mainland. And that tells us only one species arrived on the archipelago and diversified into the 13 species that we see nowadays in the Galapagos. So they've all come from a single common ancestor.
The question then becomes, how did one ancestral population give rise to many different species, each adapted to a different lifestyle? A crucial insight into how adaptation occurs came when the grants focused on one species on the island of Daphne Major.
A factor of great convenience for us was the small size of the island. That meant that we could walk all over the place.
Oh, there's a bird.
I'll leave that one to you.
The idea was that if we worked really hard, we could follow every individual or almost every individual.
They rose at 5:30 each morning to net the island's medium ground finches.
The beak depth is...
They measured the size and shape of each bird's beak, the bird's weight, and they tagged them for identification.
The male is 17418.
Year after year they returned, at times tracking over 1,000 finches.
So here's an example of a bird we know intimately over the whole of its lifespan. The number is 5960. We know how many times it bred, which years it bred in, how many mates it had, how many offspring it produced, and then how many of those offspring themselves survived long enough to breed.
Over the first 4 years, little seemed to change. Then in 1977, a terrible drought began.
Virtually no rain fell for the next 18 months.
The vegetation practically disappeared, apart from a few trees without any leaves, and of course the cactus bushes were still there.
Now the medium ground finches had to compete for scarce food.
They started off with a big food supply of small seeds, medium seeds, large seeds. As these small seeds became very scarce, they had to turn increasingly to the large and hard seeds. Well, only birds with large beaks can crack open these woody, spiny fruits.
The birds with the smallest beaks had the most trouble.
They were scraping about amongst the rocks, and their plumage got so worn that they could barely fly.
That year, over 80% of the medium ground finches died.
We would go around looking for birds that had died, and it's very sad to pick up a bird and say 3972. Oh no, not that bird. Oh.
When they inventoried the surviving medium ground finches, they discovered that one trait had made the greatest difference between life and death.
Well, I'm showing here a distribution of beak depths of the population in 1976. The survivors of this group are shown in black.
Oh. So the larger the beak, the better your chances.
The larger the beak, the higher the likelihood of surviving through the drought of 1977. 18.6 grams.
When they looked at the offspring, they found an even greater surprise. The average beak depth was more than 4% larger than the previous generation. Natural selection had changed the average beak size. Could you have ever imagined measuring and observing something like this on such a short time scale until you actually did it?
When we started, the answer is no. We could not imagine we would be able to do it.
But was this a fluke? Or are changes like this happening all the time? 5 years later, in 1983, an unusually strong El Nino brought 10 times more rain than normal. And the island was overrun by vines that covered even the cactus. The rains changed the vegetation on the island, such that 2 years later, when drought struck, larger seeds became scarce. The birds with larger beaks now had difficulty picking up the more abundant food, the small seeds produced by the vines. That year, many more finches with small beaks survived, and their offspring inherited smaller beaks.
So the selection had swung in the opposite direction, and evolution had occurred as a result.
In an amazingly short period of time, the Grants had measured evolution of beak size not once, but twice, demonstrating that when birds encounter different environments, they will change over a very short amount of time.
Over millions of years, changes like these, occurring throughout the Galapagos, generated all sorts of beak sizes and shapes. But that's only part of the story. How did finches with different beaks become distinct species? Species are defined as populations whose members don't interbreed.
So how does one species split into two? A typical scenario is that two populations become separated geographically and undergo enough change in their respective habitats that if or when they come into contact again, they do not mate.
So in the Galapagos, the Grants asked, what keeps different species of finches from mating?
We were very conscious that on any given island, the different species sing very different songs. This is what a cactus finch sounds like. Whereas the medium ground finch sounds very much like this.
So to see if songs keep the species apart, the Grants and their student Laureen Ratcliffe played each species' songs through a loudspeaker.
When we played back the cactus finch song, cactus finch came to the loudspeaker and the medium ground finch completely ignored it.
The males only responded to songs of their own species. The Grants looked at whether finches might also choose mates based on appearance. So they put out stuffed female specimens to see if males would respond.
Clearly they could discriminate. The male vigorously courted a female of his own species, completely ignored the other one.
The males only courted females that had a similar size and similar beak. Song and appearance both play a role in keeping different species from mating. So when populations of the same species are separated, changes in these traits set the stage for the formation of new species. The Grants have shown that both geography and ecology are keys to the evolution of the Galapagos finches. The most likely scenario is that 2 million years ago, a single finch population arrived from the mainland. When their descendants reached another island, they faced new conditions. As those isolated populations adapted to their surroundings, their traits changed. If the changes included traits involved in mating, and the populations came into contact again, they no longer mated. They had become distinct species. While unique to these remote islands, the history of the Galapagos finches offers a general insight into why the world is populated with so many species.
The more diverse the environment, the more opportunities for evolutionary change to produce those new species.
Over 150 years after Darwin first recognized their significance, these unassuming birds still illuminate how the great diversity of life arose and continues to evolve.
So there you go, Darwin's finches. That video explains so many things, and that's why I chose to not edit it down like I do just about all my other videos. So, great example of adaptation and speciation, basically something that's often referred to as adaptive radiation, where we start out with one species that then sort of radiates out into all of these other species that in this case involve the morphology of the beak as well as behaviors, including the visual appearance and the song of the males. Let's look at some other adaptation examples now. This is often known as the Jesus lizard, the Jesus Christ lizard. Its real name is the basilisk lizard, and the reason it's called the Jesus lizard by some people is it can walk on water, as you can see here, which is a really interesting adaptation. So the reason they don't sink has to do with the biomechanics of what they're actually doing with their feet, which do have some webbing on them, but it's really more how they use them in creating a bubble that actually keeps them afloat. And if they just don't do the right thing at the right time, they will in fact sink and then they have to swim. This video, nowhere near as long as the last one, really explains what this adaptation is all about.
This is no ordinary lizard. For years, cinematographers tried to capture its steps with varying success. Witnessed at normal speeds, their fleet-footed water dance leaves nothing but questions in its wake. But slowing the action lets us see why this animal's become so famous as the Jesus lizard. It starts with the unique biomechanics within the lizard's legs and feet. Every time it slaps its wide webbed foot on the water, it turns something that's fluid into firm footing. When their foot plunges down, it creates a pocket of air and force for support that keeps the lizard from sinking. And there's another trick at work here, the sideways force. Each lizard leg is pushing slightly outward. So, like riding a bike, each tilt to one side is corrected and counterbalanced. Of course, if you stop pedaling, you'll fall over. If the lizard stops running, it will sink into the water and have to swim the rest of the way.
And time for lunch. Anyway, very cool adaptation. Too bad we can't do that. Speaking of cool adaptations, gliding has evolved in certain species. In Borneo, we see it in a number of frogs. They have evolved more webbing on their feet than you'll see in non-gliding species of frogs. Now, they can't fly. I mean, this is not flapping flight, but they can leap off of something and then glide along. And the same with some lizards. They've developed the same thing, especially the one over on the right. Here's a really short film showing that guy gliding right there. So again, not flapping flight by any means, but still, they're not falling straight down. They are, in fact, gliding. One thing in particular that I think is interesting about these gliding lizards in Borneo is that they've started to diverge, and it all relates to the areas where they're found. So some are found in mangrove forests, and others are found in lowland rainforests. And it turns out that in the mangrove forests, there are a lot of falling leaves that tend to be reddish in color, maybe sometimes a little bit brownish black, but especially red. And they're not that way when they're attached to the trees. So, like in New England, the leaves will change color in the fall and then they'll fall down from the trees. And so basically what we're seeing in the gliding membranes of that population of lizards, the one found in the mangrove forest, is they've actually developed these red areas on their gliding membranes, unlike the ones that are found in the rainforest area. So, for example, these are what the leaves actually look like as they're falling, not as they're found on the trees. And again, a close-up of the reddish coloration rather on the gliding membranes. And side by side, you can even see the dark speckles that occur on both. And it's believed that the reason for this is that there are birds, especially in those mangrove areas, that prey upon these lizards as they're gliding. So it kind of gives them some protection by mimicking the leaves that are also not gliding but falling through the air in areas where these lizards happen to be gliding. So it relates to another segment that we did on mimicry, but also it's a very interesting form of adaptation, additional to the fact that these guys do have these gliding membranes, period, enabling them to glide through these forest areas. And I think one of the most amazing species in which we see this is this one species of snake. It's called the paradise tree snake. Now, these guys do hang out in trees, where you can see why gliding might very well serve them very, very nicely in terms of like escaping from predators, for example. Well, how do they do that? They basically flatten their bodies when they take off. They're not normally flattened like this, but as soon as they get airborne, they flatten themselves out and can glide for quite some distance.
One snake has become a consummate escape artist. The paradise tree snake lives in Southeast Asian rainforests. Among their adversaries is the sharp-clawed yellow monitor lizard, an accomplished snake hunter. While the tree snake can miraculously scale even vertical tree trunks, it would be hard-pressed to compete with the monitor's climbing agility. What's more, the canopy isn't continuous. Wide gaps between the trees prevent an easy getaway. But paradise snakes have found a better way. When face to face at the moment of danger, tree snakes make use of a truly remarkable defensive weapon, worthy of James Bond's ejector seat. The moment of danger has turned into a moment of flight. To really understand this pilot's technique, it's best to start at the launch. Tree snakes will move down a branch end and beyond, falling into a J-shaped bend, leaning into the incline as if determining a destination. But once it's in the air, how does an animal with an inner tube for a body transform itself aerodynamically? After launching, it sucks in its guts and flares its ribs to make a U-shaped wing. Increasing its size adds to air resistance. But are these snakes doing anything more than falling with style? In super slow motion, their flight is even more spectacular than thought. The body flattens down to but a ribbon. And they appear to be assuming a degree of control, undulating as if swimming, holding the tail upwards and twisting from side to side for balance. Literally, snaking through the air may help it achieve some steering and sail distances of 300 feet.
We cannot do that. 300 feet, I would be surprised if a human could flatten itself out to go 5 feet before just dropping straight down. This is a snake that's being released by an experimenter, so watch, you get a better sense from above. There it is, undulating its way down and just being captured by a person that's helping the experimenter out. Seahorse heads are very interesting. They look kind of bizarre when you think about it, but they actually enable the seahorse to move in on very tiny prey species without them being detected. And basically what they do is, the shape of the head, what they do, the shape of their head is an adaptation for not deforming the water too much. I mean, if you rush through water, you're creating underwater vibrations, waves more than vibrations, but you're actually putting out these underwater signals that if something that you're after can sense, they're going to move off. But the head of the seahorse is built in such a way that if they move in on the prey at just the right angle, that won't happen and they'll be able to get it. And one of their favorite meals are these copepods. The thing about the copepods is they are very susceptible to detect just any bit of water deformation. So you can see this kind of co-evolutionary situation happening where a preferred food item that can easily get away from you has, over evolutionary time, sort of forced you to adapt in such a way that you are greatly reducing the cue that they would be able to detect, namely water deformation. So look at these two drawings right here. So over here, we see a prey that does not detect the approach because the seahorse is moving in at the right angle to avoid the water deformation. The little arrows show that where that prey is located, there's no water deformation. Where the little arrows are coming off the seahorse's head, that's water deformation, but that's not where the prey is situated. Now notice over on the right that if the seahorse were to move in at the wrong angle, it is deforming the water. Again, look at those arrows, and the prey has moved off. The prey was in that little circle. So there, it sensed the water deformation. Okay, before I start this video, there's the seahorse and there's the copepod. There's two of them actually. Now, right when it begins, you'll see some initial deformation because the seahorse is starting out at the wrong angle. And you'll see that the copepod moves off. And if you look closely, you'll even see these little wave-like deformations occurring in the water. Again, this is all underwater. It's not like on the surface of the water. Now, after that, the seahorse is going to make an adjustment. And then you'll see, right before it grabs the copepod, that there you won't see any deformation in the water at that point between the seahorse's head and the copepod. So here we go, 3, 2, 1, now. You can see the deformation. Then there goes the copepod. So it's going to make an adjustment, coming at a better angle, and there's no deformation between the seahorse's head and the copepod, though the copepod looks nervous, but it's too late. Seahorse got it. Interesting adaptation. Okay, finally, I want to talk just a moment about primates because we've been looking at all these other kinds of animals. So this is interesting because we have the evolution of binocularity that then led to sociality, that then led to increased brain size. This short video explains the whole thing.
Most animals have eyes that are laterally placed on their heads, which is to say the eyes are on the side of the heads. And this provides these animals with a panoramic view. And that's really, really useful for detecting predators that may be coming from behind you. So there's a significant cost to putting your eyes in the front of your head. But the advantages are that you have better depth perception, you have better acuity. You can imagine then that once these animals evolved eyes on the front of their heads, they needed to live with other animals so that they could improve the probability of detecting a potential predator.
Group living was the primates' answer to predation. It allowed them to maintain their high degree of binocular field of vision without sacrificing safety. Their keeping watch with a communal eye resulted in an evolutionary side effect: larger, more powerful brains.
So you can see the evolution of group living. And once group living evolves, you have a strong selective pressure, or you might say that evolution favored larger brains, because that's more individuals that you have to remember.
Fossils show how the visual system of primates improved over time. Both the eye sockets and the optic nerve canal grew larger as brain size increased. Primates put huge demands on their sight, from color vision to increased binocular vision. They became extremely sensitive to the slightest change of expression on the faces of other primates. This increased need for visual processing fueled the development of intelligence.
And you can see how this sort of runaway process for group living, larger brains, avoiding predation, could give you the suite of characteristics that define the primate order to which we belong.
Well, there's so many examples that are just incredible having to do with adaptation, and I've chopped so many out of this one because it was running long. The diversity of life is just incredible, and the cornerstone of the diversity are the various adaptations that animals have evolved in order to compete successfully and adapt to local circumstances.